Hi everybody and welcome back. So in the last pair of videos that I released, I kind of went over some of the theory of a block diagram of this type of OCL amplifier, and then we went and actually looked at the schematic and kind of described each part a little bit. And this is already built, as I said, and I made this exactly the way it came in the package. And by the way, I was able to find these. They are still being sold online. Quite a few of them after looking around. You just have to search for OCL stereo amplifier or something like that, and these will pop up. This is not something that you want to buy and expect it to be some great thing. Go buy yourself one of those cheap Class D amps. They're more powerful and they're less expensive, and if that's all you're looking for. This is a platform to learn electronics, is the way I'm looking at it, and to learn how these types of amplifiers work if you're interested in servicing direct coupled amplifiers. So anyway, this is assembled. I used all the parts that came in the kit. I know there's been all kinds of comments about the cheap Chinese parts and this and that and fake, and we're just going to go through this and we're going to test it as it is. We're going to see all of these rumors that we hear, how much of them hold true. If some of them are not as bad as we think, some of it is worse than we think, we're going to find that out by using this as it is. And we're going to actually take the measurements and prove right, wrong, what is good, what is not good, what works, what doesn't work. That's my plan. And then each video after that, I'm going to do small sections where we will make one improvement or one change and then observe how that change affects this or doesn't affect this. So that's where we're going with this. Now, the only change I've made to this from its original design was it came with this little header pins for the input, and I wanted to be able to quickly plug in. I didn't have any of these connectors, so I changed it with a different type of connector so I can plug an RCA cable into there very easily and unplug it. That's the only modification I've made to this. Not changed anything else. These are all the parts from the box. I've added a couple of leads so we can connect either a dummy load or a speaker down the road here when we get to that point. And I don't have an 18 volt or a 36 volt center tapped transformer, which is what they're recommending, anywhere from a 12 volt, 24 volt center tap to 36 volt center tapped. I didn't have one. So what we're going to do for just the initial testing is I am going to use my benchtop dual power supply. It's got a plus and minus power mode that I can set up, and I can, if you feed a DC supply into a rectifier diode like this, into a bridge rectifier, all it is going to do is if you put DC plus, minus, and ground, it'll just use two of the diodes. The other two will block, and they'll just pass through. And the only downside of it is you'll have two diode drops on each side for each power supply. So you'll have, about 1.5 volts of voltage drop. So in order to, if you wanted to have 12 volts, let's say, out here, you'd have to put 14 volts on this side, and then through the voltage drops of the diodes, you get what I'm saying. No big deal. The main thing is we just don't want to have more than about 18 to 20 volts. Once you start getting beyond that, we're going to find out later on why you're really getting beyond the limits of the components on this board. I'm not saying the components are junk. I'm not saying that they're good. I'm just saying that the components, the actual ratings of them, we don't want to exceed them. So that's what I'm going to do. Let me hook this up, and then we'll take our first test. Alright, you can see I have my 3 power wires connected, and they are going over to this power supply right here. I'm going to turn it on, and you can see it'll have a positive and negative voltage, and these are the 3 leads coming out. It's set in tracking mode, series tracking mode. So this center, these two are tied together now, so this will be your 0 volts. and then this will be your negative voltage, this will be your positive voltage. So as I rotate this, you can see it'll add power to it, and I can monitor the current to see if there's any shorts or anything. And that's really important because we just don't know how this is going to work. The first one of these I built several years ago had issues, and some of it was related to components and things. So let's see where we are with this and if this is any better. Okay, first things first, let's apply power to this and just bring it up slowly. I have the power supply turned on, but the voltage is turned all the way down right now. And we're just going to bring it up to maybe about 5 volts. And we're going to see, first of all, we're going to measure our power coming in, plus and minus 5. And then we're going to see if we're getting that voltage drop across this. You can see right here, we'll just check it. We'll go, maybe we'll just go across this, or we'll go like from the collector, we can go to ground, and then from the, where else can we go? We go from junction of R19 and R25 and check that to ground. And just make sure we have our positive and negative 5 volts at that point. And then we're going to measure for offset, for DC offset on the speaker terminals. So let's turn this on. I have this just tied to the ground lead down here. And let's go up to 5 volts. I'll go on the positive lead first. We'll bring it up to 5 volts. And there's no current at all being, there's absolutely zero current showing up. My power supply can only read a minimum of 10 milliamps. So there is less than 10 milliamps of current. That's good. There's no shorts. And for our negative, we have negative 5. So plus and minus 5. Now if we look at the case, or the collector, which will be the case of either Q11 or Q12, we can directly read our plus VCC after it goes through this, of course. So we'll see about those voltage drops, right? So here is Q12 and Q11, so we can touch either one of them. And you can see we have 5 volts coming in, almost perfectly 5 volts, and you have about 4.5 volts. So you have that voltage drop of the diode in your bridge rectifier. And you'll also see a negative voltage drop as well for the negative side. So if we look for R19 and R25, let's see here, or R20 and R26 down here, where they meet, same thing. You have about 650 millivolts drop, which is one diode drop. So we have voltage, and it's where we want. So let's get exactly 5 volts after the diodes. So we'll turn it up a little bit till we get that. It's really touchy. That's pretty close, huh? Okay, close enough. And now let's look and see. And again, the speaker terminals on this are just referenced directly to ground. See that? Here's your negative speaker terminal. There's ground. Negative speaker terminal, ground. So I can just leave my negative on my meter there. If I go to here, and look what I have. I have negative 1.8 volts of offset. And there's no DC offset adjustment on this. So this is a terrible design, huh? We should probably not use this. It's garbage. Or these cheap fake transistors. And look, strangely enough, both channels are acting the same way, huh? This one's a little different, but they're both negative voltage, right? So what do you think that is? Do you think we should start troubleshooting this? Let's turn our voltage up a little bit more. And we'll just take our voltage up. Let's go to 8 volts. There. Ooh, what just happened? Now all of a sudden we only have 25 millivolts of DC offset. How about this side? 22 millivolts. 23. Let's bring it up to 12 volts. And look at that. As I hit the camera, it drops even more. What's happening? Look at that side. 6 millivolts of DC. That's pretty good. Even with ones that are adjustable, that's not bad. Okay, I have 12 volts. Let's see if we can get 12 volts at the transistors. Let's see. Oh, good grief. Come on. There. And what do we have? Look at that. 10 millivolts. That is quite acceptable. How about this one? 15. So that's anything under 50 millivolts is really not going to hurt your speakers or anything, and that's not bad, considered bad offset, especially with these lower end amps that don't have an adjustment. Remember, even the Pioneer SX450 that's regarded as a good low powered receiver, they don't have the adjustment for DC offset. They just rely on the input pair to be properly biased and the transistors to be okay. Now remember, I just threw these transistors in. They're not matched. Completely unmatched. So, you know, who knows what they are. And these transistors, by the way, are not low noise audio transistors. They're just a standard 9012. They are epitaxial process, you know, built, but you can see the 9012 is the PNP, and the 9013 is supposed to be the NPN, but in this one, they're using 9014s. And if we look that up, the 9014, do I even have one in here? Yeah, 9014 is actually a lower powered version than the 9013. It's a little bit different. You can see this one's only good for 100 milliamps collector current. This one's good for half an amp collector current. So yeah, they're not even a complementary pair. And you can see, I mean, this one, collector emitter is maximum of 30 volts. So you really can't put a big power supply on this or you'll exceed these transistors. These are transistors here, these outputs. These are used, as you can see, for horizontal output on the old 1980s portable black and white TVs. And they're only a 50 watt transistor. Even though they have a high voltage, they have low current, 5 amps. Like if you look at a 2N3055, it's going to be more like 15 amps or 10 amps. So again, but for what this is, you can see the circuit works very well. So let's just take 1 second before we move on and ask, why did this thing have so much offset when we went down to 5 volts? I mean, if I go back down here to 5 volts, you can see you get quite a bit of offset in there, don't you? That's pretty bad, huh? 3.6 volts negative. Well, it's because it's the way these amplifiers work, and it has nothing to do with this being cheap components or a bad design. When these things power up, as they go on, one side, because this is a complementary, or this is a push-pull design, so you have 2 transistors, one handles each half cycle. One is for the positive going, this one's for the negative going. One transistor will actually begin to turn on before the other. It's just the way that the circuits are designed. It has a little bit to do with your drivers and so forth. And so as this thing's coming up through its power up sequence, coming from 0 volts up to the 18 volts or so it's supposed to be, at the very low voltage, one side will be turned on and the other will not, and you'll see that difference on your speaker terminal. And this is what causes that thump when you first turn on an amplifier, that loud pop. Anytime you don't have a speaker protect circuit where you have that relay that's in between the amplifier and the speakers, That relay, if you ever notice, you never hear that click until a couple seconds after you turn the amplifier on. So you turn the amp on, a couple seconds later you hear click, that's the relay come in. That delay is to allow this power to stabilize as the thing powers up. That is normal. That is not abnormal. That is a normal function of an amplifier. And I just mimicked that by holding the voltage low where one transistor was on and the other was not on. That's why. So the reason you use that relay is to prevent that thump. Do you ever notice on smaller receivers or lower cost ones, when you turn them on, you always hear that thump? That's why. They don't have speaker protect circuits. This one does not either. So just a little side note. Okay, let's take a couple readings on some voltages here at the front end. Let's look at this input pair and kind of see how this thing works by taking some voltage measurements. The first thing we're going to do is we're going to take a look at R5, and don't worry, I'm going to write all this stuff down. We're going to look at this 4.7K, and this is going to be the resistor that feeds your input transistor. This is for the feedback. This is for your Class A input. So if we go across that 4.7K, and that's going to be R5, right here, we have about 633 millivolts. 634, let's say 634 millivolts. All right, and that means about, let's see, about 135 microamps of current. So it's very, very, very low current. If we look, and I'm going to write these things down on another copy of the schematic. If we measure from here to here, now remember, this is grounded through a 33K resistor. What do you think that would be in here? Do you think this would be turned on? Obviously has to be, because you have current flowing through here and there's no voltage up here. So how is this turning on if there's no voltage being applied to the base? Let's see. So there shouldn't be any drop, there should be nothing here, right? Let's measure it. Q1. That's this one here, and we'll go from the base to emitter. We'll look at the base and emitter. So I'll put the positive lead on the base. Yeah, I think that's the base, and this is the emitter. I think it's emitter base collector. And look at that. You have about 588 millivolts right there. So we'll write that down. And then if we look at the tail resistor, which is R7, that's going to show the total amount of current between both of these transistors combined. And that's a 33K, so let's measure the drop across that resistor. So R7 is right here, and that is, let's see if I can get on it correctly. I'm not reading it. There we go. 11.39. Okay, so that's 11.39 across there, and that's going to be 300 something microamps. And then, so let's stop right there, okay? Why? Well, we'll talk about it later. Let's finish our measurements here. Let's look at Q3 and see if it's turned on, because remember, there's no signal being applied to the amplifier, so there shouldn't be any voltage on the base, should there? And if the base isn't turned on, then how can we be getting any current? This should be turned off, right? So let's measure from Q3 base to emitter. So here's Q3. It goes emitter, base, collector. So emitter and base. And look at that, 599 millivolts. This transistor is turned on. All right, let's look at that. And if that's the case, then you can't have current flowing through here on DC, because this capacitor would block the flow of DC. So that there has to be current flowing through R11. So there should be a voltage drop across R11, which is your feedback resistor, right? This is coming from the speaker terminals, and there's no speaker connected. See that? It's open. So let's look at that. It's R11. Is that what that is? Yeah, 11. So that's right here. And you can see it's about 21.5, 21.6 millivolts. I don't know if you can see that. All right. I'm going to write all that down, and we'll be right back. Okay, so here is our measurements. Very sloppily written down. Let me sit down at my chair here so I can relax and do this. So here's the thing. We know that there's a capacitor here at the input, so there is no current flowing through here. And we have this resistor going to ground. So it has no voltage on it, does it? However, you have to think in terms of how this amplifier is built. This amplifier uses a differential power supply. It has a positive going power supply up here and a negative power supply down here. So you have a negative voltage on here, and you have ground here. Ground is more positive than this negative voltage. So because you're applying a negative voltage to the emitter of an NPN transistor, it can find a path to a higher voltage, right? A more positive voltage, because this is more negative, through this resistor, and current will flow. So that's how this thing's biased, through this. That's how this transistor is turned on. Does that make sense? And as this turns on, then that's going to allow current to flow between the collector and emitter, and that's what you're reading up here. So you have this 60.36346 over, which is, if you do the math, it comes out to 135 microamps. So this thing's barely turned on right now. It's a teeny tiny little signal through from collector to emitter, and it's finding its path to a more negative through this resistor here. This is your tail resistor of your differential pair. Now, in addition to that, this is connected directly to your VCC. And this is going to be what you kind of consider an emitter follower circuit. And what's happening here is, once again, through these transistors here, you are picking up your negative voltage that you need to make that reference to turn this thing, or that's more positive. I'm sorry, this is, again, this is at ground potential, because this is where your positive and negative supplies meet one another. So this center point is 0 volts, which is, again, more positive than right here. And because this is 0 volts on this side, and you have a more positive voltage on this side, or on more negative voltage on this side, current once again will flow through here, because this is more negative, this is more positive. And of course we have 599 millivolts that we measured on there, which is your forward voltage drop of the transistor. So again, you have current flowing through this loop, and you have current flowing through this loop, and then you have current flowing through these two loops, and they all converge through this 33K tail resistor for a total of 345 microamps. And of course, if you take 345 divided by 2, you get 172.5, and which would be half. So if these were both conducting exactly the same, you would have about 172 microamps, but it's a little bit lower here because of this resistor. And so that's how that works. So you have a little bit of current imbalance here. Now, the way to get rid of that would be to put a current mirror up here. A current mirror is another pair of transistors that you'll see in higher end amplifiers that will keep the current the same between the two transistors all the time. Now, because of that, you will also have down here, another thing you can do is you can replace this 33K with a constant current source, or an active current source, which would be either one or two transistors with, it could either use an LED or a diode or something. But essentially, you'd put a current source in here. So this would ensure that these two transistors can never exceed the current source, which usually they make them 2 milliamps or something like that. And you can design. It's not super critical, just so it stays constant. And then by having the current mirror up here, any tiny amount of variance you have in current here would be canceled out by the current mirror. And what that does is that gets rid of what we call common mode signal. So the idea is you want these two things to alternate. You know, as this one turns on, it cancels this out. I mean, that's the whole point of negative feedback. It's negative feedback. It's supposed to cancel some of the signal out. But what you don't want to do is, as these two voltages are kind of competing with one another, you don't want the overall current of this circuit to be going up and down. That's called common mode signal. And common mode signal will actually add another waveform or a form of distortion onto your output here, and you don't want that. Now, believe it or not, this configuration is quite good at doing that just like this with these simple passive resistor components. But if you add the current mirror and the current source, it will clean it up even more. So if you're really trying to split hairs and get as much low distortion and little bit of change as possible, you would add those two components. And maybe down the road we'll do something like that. At least maybe do a current source down here, which would help a lot. But it may not help that much. That's why we're going to test this thing as we go. So that's your input pair. That's how it works. And again, anything that you feed into here or you feed into here will either add or subtract to the already signal that's on each of these bases, which will add or subtract to what's going on in these two current paths here. And it will toggle the voltage back and forth up here. That's what's going to cause this to pass the signal into here. So I will drive a signal into here. This transistor will change. And of course, since this is a current source, as this turns on more, this will not turn on more. There will be a difference in current a little bit up here, but not bad. You'll get feedback from this as the amplifier turns on through the speaker. It'll feed back here. It will turn this on, which will oppose this, although it'll be a lot lower signal than what this side is driving. So it will, and that's all controlled by this network right here. So frequency and amplitude comes into play there. And then this is your output to your voltage amplification stage, and we'll talk about the VAS stage in the next video. But that's what's going on here. And again, we'll take some measurements with signals after we do that for the rest of the amplifier. So that's the end of this video. I wish you all peace, joy, happiness, and good health in your lives. And next time we'll take our measurements. We'll start right here.